This problem, except that the plane of symmetry will be used because this object is accelerating in the x direction. There is a plane of symmetry, and that is xz. So I have to cut this cylinder with the xz plane, and the same thing with the shell. So we are already sitting at wireframe and surface design. So we might as well use the saw and cut this with. Let's try it again. Here's the saw. Cut the shell, cut the plate with that plane, and we keep that side. Oh, how about the other side? Okay, let's keep the other side. Fine. Now, in order to cut this, we cannot use the saw here. So you have to go to wireframe and surface design because it's a solid block. Find the saw. So the splitting is done with that plane, and we're going to keep the other side. Okay, there we are. Now, for these lines, we don't have to worry about it. We just leave them. It's just that we're not going to mesh it. Okay, if you're not going to mesh it, then don't participate in the finite element calculation. We just mesh these two bars. Okay, so let's go to generative structure analysis. Immediately, CATIA meshes the block. Let me change the rendering here. Right there, see that? Okay, and then just try to mesh the shell. And I think I used 0.2, something like that. Okay, good. And then we're going to mesh, let's give it a thickness too. It's the same thickness that we had before. And now we're going to use a beam element. We're going to mesh this. Fine. And then we're going to mesh this. And that's fine. We're going to give it 1D properties, same properties that I gave to the full model. And here. Okay. Let us apply our restraints. So user-defined restraints. These uncheck all of these. Uncheck all of these. This edge is the edge of the plate and lies in the xz plane. So immediately you say there is no displacement in y, and rotations are opposite. Okay, and then you have a surface slider on that face of the solid. Simply, it's a fancy way of saying there is no displacement in direction y. Okay, what else do we have? All right, so now we're going to create connections. So connection between, let me hide this, between this point, this vertex, not point, and bring this thing into the show mode. Let's hide the line, hide the connection, the white dot. Select that point, that vertex, not point. If you put the stuff on point, it's not going to run. You already know that. What else? Another connection between, let me hide the plate, and for the second component, bring the plate in the front, hide the line, hide the dot, select the corner point, and both of these that were created are going to be rigid. Vertex to vertex must be rigid. Okay, and then we create a connection between the bottom of this cylinder and the top face of or the face of the shell. So first component is this, and then we're going to hide that. For the second component, select the bottom of that. Okay. Let's bring everything in the show mode. And show. Okay, now the load. The load is acceleration, and the acceleration on the entire part body, which you can either select it from the tree or from the screen. And in the negative direction, just remember negative direction. We discussed this thing in the earlier one. The reason it's, although this structure is accelerating that way, because we're solving a static problem, the acceleration, maximum acceleration, is acting in the opposite direction. Imagine that you're driving the car is accelerating. The force that your body is in the opposite direction. That's called D'Alembert's principle. So we say, all right, and then we're going to run it. Don't worry about the, something, yeah. I created the connection. I forgot to say it's fastened. So in fact, you can see what happens. I forgot to fasten these two. If you look at the deformation, it's going to move as a rigid body probably somehow. Let's see now. Let me change the scale here. Did I declare it as fasten? I don't think so, but it's hard. Let's see now. Maybe hard to see here. I already warned you that sometimes this will not tell you what the whole story is, but I'm pretty sure it's because these are not fastened. Okay, so let's make it fasten, and this last one that I created is fastened. It should work now. So let's run it. CATIA can help you to understand what's going on, but it doesn't always tell you that. Some of the, yeah. I forgot to put clamp at these endpoints. Let's try it now. See whether it gives us a clue what happened. No, it doesn't give us a clue. Well, why this is happening is that we forgot to clamp the ends of the bar. See, it's so easy to miss these things. Where are the two lines that are hiding? I need them. This line I want, and this line I want. Okay, let's go here. So I need a clamp at this point and that point. In fact, you can see that there's a clamp sign here, but because of the size of these things, it doesn't always do a good job in displaying what's going on. So let's give it one more try. I'm sure it's going to work. You should be prepared for glitches like this on the test. Okay, so let's look at the deformation. Change the scale to default. There. Okay. This is exactly what happened with no planes of symmetry. Okay. Same thing with displacement. Average ISO. Change the rendering to material shading. Same thing. I mean, remember, you have to check your numbers here. Check the number for stress. Make sure they make sense. The way I'm doing these problems is by showing you the process. I leave the verification and whether they make engineering sense or not entirely up to you. You have 3 years of engineering education. You should be able to use your judgment to see whether they're right or not. And for not everything, we have analytical solutions that we can compare to. All right? All right.